welcome to the deep dive. Today, we've got something a little different, something really specific and I think fascinating. We have a stack of lecture notes, and our mission is to take you right into that classroom, pull out the core engineering wisdom, and, save you the hours of studying. The material we're exploring today comes from the Electronic Design Workshop, the EDW course for fourth semester ECE students. Specifically, it's from the fourth class in that series, which was conducted by Dr. Donna J. Gadre. And we're going to be zeroing in on components that, well, they look simple on a schematic, variable resistors and capacitors, but they hide all this surprising complexity, some real-world danger, and even some mandatory professional design secrets.
That's really the fun of electronics, isn't it? The gap between that ideal symbol you draw on paper and the actual physical component you have to solder onto a board. That's where all the real engineering challenges and the solutions live. So I think the plan is we'll quickly wrap up the resistor family and then spend most of our time on capacitors. We'll look at why there are so many types, why they can sometimes explode, and how to use them for the really critical task of noise filtering.
Okay, let's do it. Let's jump into that variable resistor segment first. Now, when I think of variable resistance, I immediately picture that big, clunky thing from a physics lab, the rheostat.
The rheostat, yeah. It's really a relic of the lab, built for high current, rough adjustments. We're talking a ceramic tube wrapped in nichrome wire with this heavy metal slider making the third connection. It's great for demonstrating principles, but the moment you need to put variable resistance into a practical circuit, it's just completely impractical. The size, the bulk.
So if the rheostat is let's say, the benchtop behemoth, what's the solution when a designer actually needs that control in a final product?
Well, then you move to the potentiometer, or pot for short. The pot is designed from the ground up to be the variable resistor inside a circuit. And the key difference between them is really all about precision.
And that breaks down into single-turn versus multi-turn pots, right?
Precisely. If you look at an old school volume knob or maybe the coarse voltage adjustment on a lab power supply, that's a single turn pot. They cover their whole resistance range, say 0 to 10 ohms, in less than a full rotation, usually about 270 degrees. It's fast, it's easy.
But the trade-off there is resolution. If you need to dial in a circuit perfectly, just a tiny nudge on that knob could change the resistance way too much.
And that's a huge design challenge. If you need that high spatial resolution, for sensitive lab gear or calibration, you have to use a multi-turn potentiometer. They're really quite ingenious. They use a worm gear mechanism inside, so you might need 5 or even 10 full rotations of the knob to cover that same internal range.
So you get massive control. It allows for that extremely fine tuning.
Exactly. You'd use one to calibrate a sensor circuit, but you'd never put it on a radio. It would take forever just to turn the music down.
Right. And the source material also mentioned a third type, which is sort of defined by how it's used, the preset resistor.
Yes, the name says it all, a preset.
So a preset is basically a variable resistor you adjust once and then just leave it alone.
It is. You set it during manufacturing or maybe calibration to get the exact bias you need. It's not for the end user. Once it's set, it stays put. And that kind of completes the whole picture for resistance variation.
Okay, that wraps up resistors nicely. Let's pivot now to capacitors, the component that really defines charge storage and filtering. And with capacitors, we're suddenly dealing with a much, much wider range of materials than with resistors.
And that difference really starts with the basic physics, the fundamental equation, C equals epsilon A over D. That's where it all begins. So capacitance is set by the area of the plates, A, the distance between them, D, and critically, the permittivity, epsilon, of the dielectric material you sandwich in between.
And unlike resistors, where it's mostly carbon or metal film, the variety in capacitors just explodes because you can experiment with almost any non-conducting material as a dielectric. Paper, air, ceramic.
The dielectric choice is everything. It determines capacitance, voltage rating, temperature stability, all of it. And the lecture notes specifically called out mica, which is a fantastic case study.
What's so interesting about mica is that duality it has. It's an excellent conductor of heat, but at the same time, it's a terrible conductor of electricity.
That combination makes it perfect for places where high voltage and high heat are living side by side. The example given was insulating heating elements, like in a big industrial furniture press. You need the heat to get out to do the work, but you absolutely have to insulate the 220 volts from the metal chassis, to prevent shorts and keep people safe. Mica does both jobs perfectly.
That makes sense. But for most charge storage applications, like in power supplies, we hit a really critical distinction: polarity.
Right. If a capacitor is nonpolar, like a ceramic one, you can connect it any way you want. But if you need huge capacitance values, you have to use electrolytic capacitors, and they are inherently polar. They have to respect the voltage polarity. The side marked negative must go to the lower potential in the circuit, period.
And if you get that wrong, it's not just that the component fails, it fails violently. The source material even cites a classroom demo where reversing the polarity on a tiny 1 microfarad capacitor led to a quick, dramatic blast.
Oh, yeah, it's a real physical risk. When you reverse the voltage, you're basically destroying the very thin insulating oxide layer inside that was formed during manufacturing. It starts a chemical process, generates gas, and the internal pressure builds up incredibly fast. A 1 microfarad cap makes a pop. But imagine doing that with a 10,000 microfarad capacitor. That is a serious explosion risk. You have to respect the markings.
And that leads us straight to the concept that separates the schematic from reality, the equivalent circuit. The reason they behave this way is because they aren't just ideal capacitors.
No physical component is perfect. So to model a real capacitor, engineers use the equivalent circuit. This means you take your ideal capacitor, C, and you add 3 parasitic elements. A small series resistance, RSC, a small series inductance, LSC.
And a big shunt resistance, RSP,
Right.
which is for the leakage current.
Correct. And since it's very large, we often ignore it. But those 2 series components, RSC and especially LSC, they are the Achilles heel of a capacitor, especially at high frequencies.
Why is that inductance so bad?
Well, think about how large capacitors are made. They're not 2 simple plates. They're usually long foils of metal and dielectric, all rolled up like a scroll to maximize the area in a small space.
A coiled wire, that's an inductor.
It is. And the longer the winding, the higher that parasitic series inductance, LSC.
So when we're trying to use a capacitor to filter high-frequency noise, which should have low impedance, that hidden inductance starts to fight back.
Precisely. The capacitive impedance, XO, drops with frequency, which is what you want. But the inductive impedance, XL, increases with frequency. At a certain point, the self-resonant frequency, they cancel out. And above that frequency, the component you thought was a capacitor actually starts behaving like an inductor. It blocks the very signals it's supposed to pass to ground.
Wow, and that limitation brings us right to their main application: charge storage and smoothing voltage in power supplies.
Exactly. Power supplies need huge charge storage to keep the DC output smooth after rectification, whether it's half wave, full wave, or a bridge. And that smoothing path needs huge values, 1,000, 10,000, even 20,000 microfarads.
And as we just said, to get those massive values, you're forced to use electrolytic capacitors, which are polar.
It's the only way. And designers have to account for that polarity and also for things like the voltage drop across the diodes and the rectifier. 1 drop for full wave, 2 for a bridge. You need all that to choose the right components.
Okay, so this whole discussion about parasitic inductance sets up what is probably the single most valuable design secret from that lecture: the noise filtering topology. If you look at any modern digital circuit board near an IC, you will almost certainly see 2 capacitors in parallel on the power pin.
Yes, this is the standard mandatory solution to that LSC problem. You use the big electrolytic, say 10 microfarads. Its huge capacitance is great for handling low frequency ripple and big power fluctuations. But because it's physically large and coiled up,
Its series inductance is high, so it's useless at high frequencies.
exactly. So you have to add a smaller ceramic capacitor, often a 0.1 microfarad, in parallel with it.
And why that specific one?
The ceramic cap is tiny, short leads, simple construction. That means it has a very, very small LSC, so its self-resonant frequency is much, much higher. It's terrible at the low-frequency stuff the big cap handles, but it is fantastic at shunting away those really high-frequency spikes from digital switching that the big electrolytic completely misses.
So that pairing, the 10 microfarad and the 0.1 microfarad, is the professional standard for power supply decoupling. It covers the whole noise spectrum.
It's the essential compromise. And, while we're on it, we should mention tolerances. Resistors can be very precise, 1%, 5%. Capacitors are much worse. 20% is common, and 10% is considered pretty good. You have to design for that wide variation.
So beyond power supplies, what are some of the other key jobs capacitors do?
Oh, they're everywhere. They're essential for low-pass and high-pass filters, which are really just integrators and differentiators. They're used for coupling signals between amplifier stages, letting the AC through while blocking the DC bias. Also for things like voltage doublers, and of course they are fundamental to creating frequency in oscillators.
And that brings us to the extreme end of the scale. Supercapacitors. We were talking about maybe 20,000 microfarads being big. Supercaps start at 1 farad.
Yeah, and they go up to hundreds of farads. Their potential is massive, especially compared to batteries. A key thing is their longevity. They can be charged and discharged tens, even hundreds of thousands of times. A typical lithium-ion battery is dead after about 1,000 cycles.
So they're ideal for things needing repeated, quick bursts of energy, like in an electric vehicle's braking system.
Absolutely, they have much higher power density. But the limitation is still energy density. They store way more than a regular capacitor, but they're still nowhere near a chemical battery for total energy storage. So for now, they're mainly for short duration, high power jobs.
We've gone from a bulky lab rheostat to the future of energy storage. This has been a really great deep dive. For you, the listener, I think the critical takeaways are threefold. One, always respect capacitor polarity. Two, understand the high-frequency limits from that parasitic inductance, LSC. And three, remember that professional trick of pairing a large electrolytic with a small ceramic capacitor for noise filtering? It's universal.
And if we tie this all back to oscillators, the theory that governs all of it is the Barkhausen criteria. For an oscillator to sustain itself, the amplifier's gain has to be enough to overcome all the losses in the feedback loop. The overall loop gain has to be 1 or slightly more. That's how filters become clocks.
Right. So we discussed the Barkhausen criteria for oscillation, but the lecture notes also hinted at something else, the Barkhausen effect. We've spent all this time talking about digital noise and the non-ideal behavior of components. So here's a thought. If knowledge is most valuable when it's applied, what connection do you think the physical phenomenon of the Barkhausen effect, which is all about magnetism and material noise, has to the noisy, power-hungry electronics we've just discussed? Something to research until our next deep dive.